I'll get in the groove, I think.
All right, Mark, Kevin, you got this?
Yes, we're rolling.
Okay, I can put this
Can you hold
down.
that higher?
Yep,
That's good.
good?
Yep.
Okay. All right. Good to go? Okay.
Okay. All right, let's get started. So, Matt, what role does temperature play in UTC? Why is this part of the UTC?
So a big part of what we do as a company is maintaining temperature at a comfortable level. So for example, our carrier business unit, they're in the business of maintaining temperature. So on a hot day, it's a nice comfortable temperature in the office. Likewise, on a cold day, it's a nice comfortable temperature in the office. The produce in your supermarket is kept at a safe temperature, nice and cold, both in the supermarket as well as when it's in transit to and from the supermarket. So it's a huge portfolio of products to help maintain comfortable temperatures, safe temperatures, and so on.
How does that kind of change the way the world lives?
It's really enabled us to inhabit the places on this planet that were previously uninhabitable, or at least to inhabit them comfortably. So the southern United States, or the southern parts of the country, or the equatorial climates, as well as very cold climates, these things all become new places to live and work because of our ability to maintain comfort inside the buildings.
So we're also traveling in environments that human beings have never traveled before, like 30,000 feet over the surface of the Earth. How is UTC involved in making that possible?
So if you're on a plane at, say, 36,000 feet, that environment up there is essentially inhospitable to human life. So, we have the miracle of air travel, but at the same time, it's really become possible because of our ability to maintain a human-friendly climate in those atmospheric regions. So our UTC Aerospace business unit and their air management systems that pressurize the cabin and remove ozone and maintain a comfortable pressure, temperature, and humidity inside the cabin are really enabling long-haul flight today.
What are some of the challenges that you still face in that environment? It's kind of things we're kind of working on inside.
So if you think about it, if you're on a plane, we still don't feel particularly comfortable in that environment. It's a little bit of a lower pressure than we're used to. It's certainly a lower humidity than we're used to. And so there's still work to be done to improve things further.
So we're talking about two environments. There are some even far harsher environments where UTC is making life possible. Can you talk a little bit about that?
Sure. So some examples would be in outer space or in submarines. So those are the two environments. Let's take, for example, outer space. You just have to. You're basically providing a life support function at that point. You're providing the atmosphere to enable a human to inhabit that environment. So it becomes critical, because if you're not involved with that, then it just would not be possible.
And what are some of the kind of additional challenges of an environment like that where it's 100% atmosphere?
Good question. So I would say it's you have to get it right 100% of the time, because you're the only thing there maintaining that life, and so it becomes a mission critical aspect.
Is there something to do with the fact that they have to breathe the same air? Or how do you deal with moisture and balance that, all the byproducts of existence?
Sure, you're basically in a sealed chamber, so you have to recycle. You're resource limited, so the carbon dioxide you breathe out, you have to treat that air and restore it to a breathable condition. You can't just dump it overboard and expect more to show up.
We're talking about changing the environment. The instruments in the exhibit are pretty much have to do with sort of measuring temperature, humidity, atmospheric pressure. In other words, understanding the environment as it existed, not changing. Why is that necessary?
So I think if you look in a lot of science areas, not just in temperature, as humans and as a society, we've tried to understand something before we've then tried to control it or make it better. So in the example of temperature, we try to understand temperature, understand how to measure it, ways to measure it. Once we succeeded in doing that, then we moved on to, well, we're not really satisfied with how the temperature feels right now. What can we do to change that? And for that, Willis Carrier, I think, was instrumental.
What did Willis Carrier come up with? What did he see and what did he do to change?
So he basically invented the modern air conditioning system, which on a day like today is the reason we're comfortable in here. Well, maybe not today, but in general. And so he basically invented that system, which is now used worldwide to maintain a nice environment in your office or your home. The other thing he did was a lot of work on understanding the relationship between temperature and humidity. And so you'll find it can be a hot day, and if the humidity is low, you're still quite comfortable. Likewise, it doesn't have to be particularly hot. If it's close to 100% humid, for you to feel kind of sticky and a little bit uncomfortable. And so he started to recognize this interrelationship, not just on how it related to comfort, but then how to make things better and improve things.
And what did he actually?
Actually, if you just slide a little bit,
Sure.
right back over.
So what did he actually do to change that environment? What did he invent and come up with?
He invented the modern air conditioning system. So it was a system that would remove moisture from the air as well as reduce the temperature. And that's the basis for climate control systems today.
How do you do that? How do you remove moisture and change them?
So they're related. So the way he and the way it's done today is you drop the temperature of air, and as you drop the temperature, the humidity, the air is no longer able to hold as much humidity, and so some of that humidity falls out. You'll see it in your air conditioner at home. Your indoor coil is dropping moisture, and then that cold air is then circulated throughout the house. The working principle behind that is a vapor compression system. And so you have a working fluid, a lot of the refrigerants today, and you compress that and you remove heat from it, and then you expand it, and then you use that expanded cold fluid to provide cooling to your home. And that fluid flows in a cycle and runs continuously.
So let's talk a little bit about temperature itself and some of these instruments that were developed to measure it. How does that work? How do you measure temperature? Why is the progression of different instruments exhibited?
So, I mentioned how we tried to understand temperature, and temperature is sort of this abstract thing. You feel it, but it's very abstract. And so what people have done is look at the effect of temperature on something. And so a lot of the temperature measurement exhibits look at different ways that temperature will affect something else. And then that effect can be something you can see or measure. It allows you to quantify temperature for the first time.
Can you describe one of the instruments, say the bimetallic thermometer? How does that work? What are they observing?
Sure. So a conventional thermometer looks at how temperature affects a fluid. It used to be mercury inside a glass tube. And so as the temperature increases, the mercury would expand and rise up the glass tube. That's a thing you can see, and it's a thing you can measure. The bimetallic thermocouple looks at temperature's effect on something else. It's two different metals that are placed next to each other. And so one metal will expand more than the other one as the temperature increases. And so that creates a mechanical displacement. And again, that mechanical displacement is something you can see, and then you can use that as a measurement for temperature.
Is that related to anything we use today, any kind of instruments or
So a lot of thermostats in the home actually still use a bimetallic strip as the means for cycling on and off an air conditioning system.
And what came next, a thermopile?
Yeah, so the thermopile I find really interesting because it's basically the basis for a lot of measurements that we do today. So rather than using temperature's effect to create a mechanical change, this one uses temperature's effect to create an electrical response. And so the way it works is you have air passing over these series of metals, And rather than looking at the displacement, you're looking at how that, basically the junction between metals will create an electrical signal for you that's proportional to the temperature at that junction between metals. And so then that gives you an electrical signal that you can read and convert to a temperature measurement. And it's exciting because it's the basis for the thermocouple that we use today. They're in labs all over UTC, as well as in products that we make. And it uses the exact same principle, that when you have two different metals that are touching, they'll create an electrical signal that is a function of temperature.
Well, let's talk a little bit about one of the other aspects of the human environment in terms of atmosphere is humidity. So there's some instruments in here in the exhibit that they came up with to measure humidity. Do you have any in particular?
Yeah, so the thing I like about some of the humidity measurements the most is the concept of a dry bulb, wet bulb measurement. And so the way that works is you have a conventional thermometer, and that is measuring your temperature. And then you have another second thermometer that has the tip of it that you maintain as a wet condition. And so that, because it's wet, it is evaporating moisture to the environment, and that evaporation rate is a function of what the humidity is. So you end up with two thermometers reading different temperatures, and the relationship between those two temperatures gives you the humidity. So it's a remarkably simple way of measuring humidity, and it's also a very reliable way, and for that reason it's still done today. A lot of sensors that we use today use the same principle of a dry measurement and a wet measurement and looking at the difference between them. It's very reliable and accurate, and is used to calibrate other sensors that may use a different mechanism for measurement because it's so reliable and accurate.
So there's a artifact, can't even call it an artifact, there's an instrument in the exhibit that's pretty contemporary. It's called mirror for measuring dew point. Describe that.
Yeah, so it's a chilled mirror hygrometer, and the way that works is it uses a little, like a tiny refrigerator to chill a mirror. It's actually a thermoelectric is the way they do it. But you chill a mirror, and when that mirror is below the dew point, it will start to condense moisture on it. And then that creates an optical effect that you can use. And so this combination of technology, cooling something down, condensing on it, and looking at the optical properties of that condensate layer can be used to, with a lot of electronic circuitry, can create a signal that's a function of the humidity. So it's a modern measurement, it's a modern way of measuring humidity, but you'll notice that it relies on the same principle of moisture.
So is that an instrument for observing things, or is that actually employed in products?
Both. So it's used in the labs when we're trying to measure something and understand what the humidity is, and it's used in products as a very reliable and digital way to measure humidity.
What are some products that's employed?
So you would find humidity sensors in a lot of building climate control systems, where they're interested not just in the temperature monitoring, but also maintaining a comfortable humidity level.
And so they're being used in these kind of smart buildings, constant monitor and changing.
Exactly. So it's a big part of a big instrumentation network where you're trying to monitor the temperature and the humidity and other parameters throughout the whole building, and in a very smart way direct your resources to the part of the building that needs the most cooling or the most humidity control.
Okay, so just about the last question, if you're taking a friend or colleague sort of from outside the business into this exhibit and bringing it to the temperature section, what would you point out?
So I would point out the let me think about this for a second. It's a new question. So I think what I would point out to them is the fact that I think it goes back to what I said earlier. You know, so I'd want people to see that how hard society worked to understand temperature and to measure it. You see examples of several different temperature scales. There's a Fahrenheit scale, Celsius scale. Those two people are largely familiar with. There's also the Reamer scale, which has largely fallen out of fashion. You know, these things were ways to communicate communicate temperature between scientists. You know, if I say it's 20 degrees centigrade, another scientist will know what that means and understand that that's a comfortable temperature. So I'd want people to understand, you know, how hard these early scientists and engineers worked to understand their environment and to come up with instruments and devices that allow them to measure and quantify what they feel, and then their work to then improve from there and allow us to, you know, it gives the foundation to allow us to control and monitor and adjust the climate around us accordingly.
Why were they working so hard?
I think just curiosity, you know, we always, as scientists and engineers, we're never satisfied with something we don't understand. And so I'm sure people felt temperature back then the exact same way we do today. They felt, you know, hot and bothered on a hot, humid day, and they said, you know, what's going on? Why do I feel this way, and how can I understand what's going on? And so they came up with these instruments to help them quantify that.
I have a correction. I think we should go back to that statement when you described the Lewis carrier's cycles. You use the word water drop-off. I think you should use condensate. I think it's a lot better than just drop-off. I think
That's sort of where people know what they're talking about.
condensate, well,
Yeah,
since it's a technical issue, I think you spoke everything about it except that word. The word drop off is just could drop off the air or drop off the coil. So off the surface. I think if you say that the water vapor of the air touches the cold surface and condensate, and the condensation comes off of the coil, and that's what we see the water dripping out of the air. It's condensation.